In this example, we will want to solve a system of linear equations by graphing. The equations in this system are not in slope-intercept form, so that will be the first step of work that we want to do. To keep the work straight, I will end up using two colors, and I will label my work connected to either L1, meaning the first line, or L2, the second line. So the first equation is 6x plus 9y equals 18. To solve that for slope-intercept form, we will first subtract 6x from both sides. Subtracting 6x from both sides gives us 9y equals negative 6x plus 18. We will then divide both sides of the equation by 9, which will give us the equation y equals negative 2/3 x plus 2. Now while I could jump over to the graph and start graphing that immediately, I'm going to hold off to make sure I pick a scales and I center the graph where I want to center it so that it will work for both equations. So instead, I'll go over to line number 2 and label that L2, and I will take the second equation, 4x plus 6y equals 12. And we'll solve that equation for slope-intercept form as well. We'll begin by subtracting 4x from both sides, which will give us 6y equals negative 4x plus 12. We will then divide both sides of the equation by 6, which will give us y equals negative 2/3 x plus 2. Now that both equations are in slope-intercept form, I can see that if I center my axes at the center of the graph and use a scale of 1, 2, 3, all important information will fit on that graph. So we will begin by drawing both axes, labeling and scaling them, and adding arrows to at least the positive ends. Now that the axes are set up, we'll turn our attention to line 1, y equals negative 2/3 x plus 2. The 2 on the end tells us we'll start at the point 0, 2, and from there our slope is negative 2/3, meaning down 2 to the right 3, or up 2 to the left 3. Again, we can see those connect in a downhill direction. We'll finish off graphing line 1 by connecting the dots with a ruler and then drawing the line. As always, don't forget to add the arrows to both ends of the line, and make sure you label this as L1. Now we turn our attention to line 2. Line 2 we can see has a y-intercept at 0, 2, so we could plot that. We see the slope is negative 2/3, down 2 to the right 3, or up 2 to the left 3. And what you probably already recognized before we even started graphing anything is that the two equations are identical. So when I go to connect those dots with a ruler and draw in that line, not so surprisingly, it ends up being the same line. I'll still add on the arrows just to make sure they're there to represent that. But I also need to recognize, not only is that line 1, that's also line 2, so I need to label it as line 2 as well. So what does this mean for us? We had two different equations, we graphed them, and they ended up being the same line. If you go back to the fundamental of what it is we're trying to do, we're trying to find any point that is on both lines, because we're looking for any ordered pair that's a solution for both equations. Since both equations are variations of the same equation, since they have the same graph, every point on one line is going to be a point on the other line. We have an infinite number of solutions for the system. Because there's an infinite number of solutions for the system, we can't write out all those solutions. But we do need to give some sort of description. We don't just want to say there's an infinite number of solutions and leave it at that, because while there's an infinite number of solutions, there are still points that are on neither line. For example, the point 3, 4 up here is not on either line, so it's not a solution. So we do need to be somewhat precise in what we say. In this particular case, because our system has an infinite number of solutions, or another way to say that is that our solution set would have an infinite number of solutions in it, we need a way to describe all of those solutions. So we begin our conclusion by first stating this: the solution set is. And to finish this, we need to go back to our set builder notation. Set builder notation begins, as a refresher, set builder notation is constructed as follows. You start out using a set, braces, to say we're dealing with a set. There's a vertical line inside that set to separate the two pieces. On the left side, we identify what the solutions are going to look like. Another way to say that is, what form do they take? Because we are dealing with ordered pairs as solutions, the form of the solution has to be x comma y. And on the right side of the solution set, we need to list out the restrictions, what it takes to be included as a solution. So what does it take to be a solution for the system? You have to be on one of these lines. And how could we efficiently describe every point that is on either of those lines? Simply by listing the equation, y equals negative 2/3 x plus 2. So our solution set for this particular example is a set of all of the xy points that satisfy this equation, y equals negative 2/3 x plus 2. When there are an infinite number of solutions for a system, you will not typically be asked to check those solutions. For one, it's impossible to check every solution, and generally we only require you to check the solutions if there's exactly one solution for the system.